Welcome to Chapter 3, Energy. Energy is everywhere in our universe. The official definition is the capacity to do work, and that means we have to define what is work. Work is the force acting on a distance. The behavior of matter is driven by energy, so energy is crucial for chemistry students. We have the law of conservation of energy, and just like the law of conservation of matter, it means that it isn't destroyed or created. So that means the total amount of energy is constant. The amount of energy in the universe is not changing. Now, energy can be changed from one form to another, or it can be transferred from one object to another. But in ordinary chemistry, you can't create energy and it doesn't just disappear. It is not just lost. There are several types of energy, two categories: potential energy and kinetic energy. Potential energy is stored energy, and commonly when you first learn about it, you learn about energy stored to its position, the gravity. So for example, if I have this 10-kilogram weight, it has high potential energy here, and then when I drop it, it has low potential energy, and the energy has transferred not only to the air through friction, but to the surface it lands on through heat energy. What we commonly look at in chemistry is actually due to its composition, and that's the attractive and repulsive forces within the molecule. Another type of energy is kinetic, and kinetic means motion, so it's energy due to the motion of the object, and we look at that in chemistry as well. If I sum the kinetic energy and the potential energy together, I have the total energy in a sample. There are some different forms of energy. There's electrical energy, and that's the flow of electrons or electrical charge. Thermal energy is our kinetic energy, energy associated with the random motions of the atoms and molecules. Chemical energy is associated to the position of the particles within the molecule or atom. Some more definitions, some units this time. We have calorie, and that's a metric unit. Notice that it is a lowercase c, and that's the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. If you look on the back of a food package, it actually says calorie with a capital C, and that's a kilocalorie, so that means that a kilocalorie or a capital C calorie has 1,000 calories. Another unit we use more often in chemistry is the joules, and that's the SI unit. So we have calorie is the metric and joules is the SI unit for energy. It's named after James Joule, who demonstrated that energy can be converted from one type to another, and the total energy was conserved, or nothing was lost. Our conversion factor, or our equality, is 1 calorie equals 4.184 joules. Let's try a conversion. We want to change 6.0 calories to units of joules. We're going to start off with our given, which is the 60.1 calories, and then we're going to use our equality as our conversion factor. When we make our fraction, we need to have calories on the bottom so it cancels out, and we end up with joules. Notice that I have 3 sig figs in my beginning value, and so I have 3 sig figs in my answer. I also have a unit. Pause the video and try this problem. I'm going to start off with my calorie, capital letters, so I know it's really a kilocalorie, so I need to convert it to calories before I can use my calorie to joules conversion factor. Once again, my units cancel. The last unit is joules, so that's what I have here. My initial value has 3 sig figs, and my final value has 3 sig figs. If a system or a chemical has high potential energy, it tends to change in a way that makes it have a lower potential energy. That means that materials that have high potential energy tend to be unstable or reactive. So if we look at TNT, dynamite, trinitrotoluene, it has a pretty high potential energy, so there's a lot of energy in there. It's a rapid chemical change that lowers the overall potential energy, and it gives off that energy in both heat and light, and that's why it's so explosive. One thing to remember is when I have to break molecules apart, it takes energy to break those bonds, and then when new bonds are formed, energy is released. For our next part, we need to look at both the systems and the surroundings. The systems is what we focus on, and you can define this any way you like. In chemistry, we define it as molecules and elements that are reacting. Now, the surrounding is everything else. If our reactions are solutions, then the surrounding includes water. The energy given off by the system has to equal that that's taken in, or vice versa. If the surroundings are giving energy to the system, they both have to be equal. We talked about endothermic reaction. The energy is released by the particles. What this means in a chemical reaction is that the reactants start off with more energy than the products end up with, and that amount of energy, the difference, is released. Endothermic, the energy is absorbed by the particles. So our reactants start off with less energy, we absorb energy, and our products have more energy than the reactants. Here's another way to look at it. If I have particles here that are going to react, I have to put energy in to break them apart, to break those bonds. Then when they reform bonds, they're going to give off some energy, and their potential energy is going to lower. The difference between those is what is released. So this, because energy is being released, is an exothermic. Over here we have similar reaction, and the particles, I put energy in to break them apart. The new particles formed give off energy. It is not enough to offset the amount of energy put in, and so it ends up being endothermic. If we look at our graphs, this represents our reactants. We put some energy in to break them apart. New products are formed. Their energy, potential energy, is lower, and this amount of energy is released, so it's exothermic. Your graph is another exothermic. Please pause the video and quickly sketch out this endothermic. When we have endothermic, once again, we're putting energy in to break the particles apart, but the products have higher potential energy. So overall, there had been some energy absorbed, and that causes it to be endothermic. We said that our particles are in constant motion, and so temperature is a measure of that motion. It's the average kinetic energy of particles in the sample. When we take a temperature, we're actually measuring the average kinetic energy of particles in the sample, and that's very different than common use. Heat is also a different definition than common use. Heat is the flow of energy that is due to temperature difference. All energy moves from high to low areas. If I have a box of water and one side I have hot water, and it's very common to show more energy with longer particles or perhaps longer arrows. That one has more energy than the second one. The length of the arrow shows the amount of energy. In physics, that's called a vector. I have the cold water. On this side, it's only 10 degrees. Notice the little tails there are smaller. They have less energy. And so the energy is going to flow from the hot water to the cold water till eventually they're going to become the same temperature. If I'm looking at my endothermic reaction, once again, I have my chart here, my reactants, and my products have more energy, so I'm looking at the particles. If we look at the temperature, and it's very important to read your graph. This one says potential energy, this one says temperature. If I'm measuring the temperature of the water is the surroundings. The reactants are going to take in energy from the surroundings, and that includes the water. So the temperature of the water will decrease. The beaker temperature will decrease, and if you put your hand on it, it's going to feel cold because it's taking the energy from your hand and going to the particles. Right? So if the temperature decreases, it is an endothermic reaction, and all of that energy that's going in makes the products have higher potential energy. So be sure to read your graphs. The opposite is true for our exothermic reactions. I am putting a little bit of energy in to break those bonds, but then when they reformed, energy is released, and so the temperature of the water is going to increase. The excess energy is going to be given off in the water, and that's going to cause the temperature to go up. And this is what a graph looks like if you're measuring the temperature of the water How tall was the man who invented our temperature scale? He was fair in height. Daniel Gabriel Fahrenheit is the one that we're most familiar with. Scientists use Celsius because it is a scale of tens. Kelvin is actually one that is over here on the left. Take a moment and see if you can figure out the relationship between Kelvin, which was developed by Lord Kelvin, and Celsius temperature scales. If we look, they're the same size because I go from 273, where water freezes, to 373. I go from 0 to 100, and the difference is 100. But there is a big difference. I add 273 to my Celsius to get my Kelvin. When we look at gases, the use of Kelvin will become more important. So we can take degrees Celsius and add 273. Sometimes you will see 273.15. We will always just use 273. That's sufficient. And so if we need to figure out the Kelvin, we simply add that to Celsius. If we're given Celsius, we just simply solve for the Celsius. If we're given Kelvin, we simply solve for the Celsius. We're going to leave this page after we do our POGIL for calorimetry. Speaking of calorimetry is measuring the heat flow. So we're measuring the transfer of energy. And this is a very common calorimeter where you use styrofoam cups because they are good insulators. You heat up a piece of metal, a rock, an object, you put it in the water, and the temperature of the water goes up because the energy is transferred from the hot object to the cooler water.